All right, so this week, talking about rank, and the rank is a natural thing that kind of comes out of what we've already been talking about. So it says it's the dimension of the column space. So rank, the rank of a matrix A, rank A, equals, uh, we'll say dim, dimension of call A. And so why would we not just write dimension of column A when why create something brand new rank for something that we already have? Well, it's because the dimension of the column space is not just the only thing that's equal to the rank. There's a lot of other things that are equal to the rank. Here, if you look at the next definition here, it says the set of all linear combinations of the rows of a matrix. So if you take each row and you do linear combinations, you get what's called the row space of A. Now, it turns out that the dimension of the row space, so the number of linearly independent column or linearly independent rows, is the same as the number of linearly independent columns. So it says the dimension of the column space and the dimension of the row space are equal. They happen to be the same thing, which that common dimension we're going to call the rank. And that rank also happens to be the number of pivot elements. So this is the whole purpose of this of the argument or of the renaming of this to rank, because we've been talking about pivot elements for a long time now. Since chapter 1, we've been talking about the column space since this last for this last chapter that we've been doing. So now we want one word to condense it, kind of like the determinant, kind of like invertible. We want one word to help us encapsulate all of these ideas into one, and so that's the rank. So it turns out, if you remember, we had the dimension of the column space plus the dimension of the null space. We learned this last time of A is equal to the number of columns. So this is the total number of columns. And if you have any questions, you can always just ask them in the chat there, and I can see them on my other computer. So if you have a question, you're not interrupting the lesson. You can just ask them at any time. So here the rank and the column space are the same thing. So that's why we are seeing this equation here. So this is called the rank theorem, and we'll use that whenever we want to find the dimension of either the null space or the column space or the rank. Yeah, so here this is a nice little description that helps us kind of condense things. So the rank of an n by n matrix A is described in several ways. So all of these points are the same thing as saying the rank. So the dimension of the column space, that's the definition. The number of pivot positions, maximum number of linearly independent columns. So it is the number of linearly independent columns. I don't know if the word maximum here is essential. The dimension of the row space of A, the maximum number of linearly independent rows, and the maximum number of invertible submatrix. So submatrix, that last one might need a little bit of an explanation. So submatrix, if you've got a 3x3 matrix, then you say you have two linearly independent columns of this 3x3, then you could take the first four element, you could find a submatrix, you could find a submatrix that ends up giving you an invertible matrix there. I've got to close this because I lost my cursor in that little event. Chapter 4. Okay. So what is this one here? It says the effects of elementary row operations. So let's go ahead and have a look at that. So this set here, so what do elementary row operations do? They do not affect the linear independence relation among the columns. Row operations usually do, so they usually change the column space. So what that means is if you start doing row reductions, you will change um, the span of the columns. So if you're having trouble seeing that, then maybe imagine row reducing and canceling a column and getting something like this, maybe. I don't know, something like that. So this last row here is 0, and maybe it wasn't 0 in the original matrix. So the column space has changed. So you could say if this is the row reduced form, the column space has changed. But row operations never change the row space. So as I do row operations and add and subtract rows from each other, that will not change the relationship among the rows. The row space will still be the same. So this will lead to the definition of the basis of a row space, or how you find the basis for a row space. You just find the reduced row echelon form, and then take the non-zero rows to find the basis of the row space. And then the last thing, row operations never change the null space, which we found the null space since chapter 1. We found the solution set to the homogeneous equation, ax equals 0, and that the solutions to this equation are the null space. We've been finding the vectors for the null space by row reducing the matrix and then and using this to write the general solution. So that is how you find the null space, and row operations do not change the null space. So this little key here, the effects of the row operations, is really useful because sometimes it can be confusing. It's like, wait a second, did adding those two rows together really change the column space? And the answer is usually it does. If you add two rows to each other, you will probably change the column space. But you can never change the row space by doing that. Okay, so hopefully that made sense there. I know I'm jumping in, but let's go ahead and look at this theorem here. This is the invertible matrix theorem, IMT, and we're just adding on a few things here. So if the matrix is invertible, then these following things are true. So we're adding these on to the invertible matrix theorem from chapter 3. And so here, M, let's go ahead and read it. It says the columns of A form a basis for Rn. So n is the number of columns and rows. And so if the matrix is invertible, then you have a basis out of the columns. The column space is equal to Rn. So if you take the span of the columns, you end up getting all of Rn because each of the columns are linearly independent. That's because the matrix is invertible. The dimension of the column space is the total number of columns. So every column is linearly independent, which means that it's the number of, remember, we learned what the dimension was last time. The dimension is the number of basis vectors in the basis. So the number of basis vectors here is the number of linearly independent columns, which is n because the matrix is invertible. The rank must also be n, since the rank and the column space are the same thing, or the dimension of the column space and the rank are the same thing. The null space must be the set containing only 0, which means that the dimension of the null space, sometimes we call it nullity, is 0. So this is the set containing 0, and the dimension of that set is 0. Remember, the set containing 0 is not a linearly independent vector with any other vector, so this is a linearly dependent set. So maybe you'll want to write that. So linearly dependent set. So then the dimension of that set, or the number of linearly independent vectors, is 0. So that's how we can get away with saying this theorem up here. The rank, which is going to be n, plus the dimension of the null space is 0. So you have n plus 0 for the rank theorem. So you end up having n linearly independent columns. Oof. Okay, so enough reading. Let's get into some examples and see how this works. So here they give us a matrix A, and it says give a spanning set for row A. And so what this is going to be is just a row reduction of this matrix A. So let's go ahead and do that. Maybe we'll do this on a calculator to save a little bit of time, since we only have 45 minutes together, and because we don't, because we're also recording this. So let's try to do this on our calculator. So here we'll edit this matrix. We'll make it a 4 by 5. And we want -2, -5, 8, 0, and 17, -17. So each one of these rows, if we take the span of these, the span of the rows form the row space. And so what we are looking for is a basis for the row space, or the number of linearly independent rows that we have here. So let's do 7, 1, and okay, I think we're good here. So this is going to be +1, 7, and -13, 5, and now we just want to row reduce. So you could choose to row reduce this by hand, but I am choosing to spare you the details here. So let's RREF matrix A. Oops. Okay, this is hard to do with a mouse, but I'm getting there. Okay, so here we go. So let's just, on our papers over here, let's write it like this. We'll say A equals, so we won't say equals, but then we'll just draw a squiggle, or you could draw an arrow or something like that. And then we'll row reduce it to this. 0, 3, and then 0, 0, 0, 1, 5, and then here's a bunch of zeros. Okay, so now what this means is the span, so row A equals the span. Now we could write out a bunch of row vectors like this, which is kind of a pain because it starts to run off the edge of the page. So usually we don't like to write it out like that horizontally, because horizontally it just takes up too much space on the page. So what we like to do is write the rows as columns, and then just use transpose. So this transposes this 5 by 1 vector to be a 1 by 5 vector. So it's just a more compact way of representing a row. So these are the rows. I'm just writing them vertically. Okay, there we go. So this is the spanning set. So notice this is the minimal spanning set. So this is also just say also, this is a basis for row A. These are linearly independent rows. Remember, row operations do not change the row space. So these vectors form the row space. So these are the or the basis for the row space. So let's, and notice we have 1, 2, 3 pivots. So let's go ahead and answer the next one here. So it says find bases for the row space, column space, and the null space of this matrix. Sure. Okay, so first of all, we've got the basis for the row space. So we'll just say basis for row A is what we have above. So we'll just say is the set 1, 0, 1, 0, 1 transpose, and then we'll write the other column 0, 1, -2, 0, 3 transpose, and then the last column, or the last row here, 1, 5 transpose. Now the mistake that almost I have my students make the same mistake every year. I'd say everybody makes it once, but hopefully you wouldn't make it on a test, right? Would be, so this is for column column A. A lot of times what people do is they take these columns, they take the linearly independent columns, and that would be the mistake. So you don't want to just grab this column and this column and this column. That's not the row space. And remember, the reason that this isn't the row space is because row operations usually change the row space or the column space. So the reason that we don't want to take these columns is because they're no longer the vectors that we started with. What we want to do instead is correspond these pivot columns back to the original column that they came from. So these form the basis for column space of A. So we want to write those down. So let's go ahead and take those columns and write them for the basis down here. So it was the first two and the third one, or the fourth one. So the basis for the column space, we'll want to take the first one, the second one, and the fourth one. Now, does this mean that this vector here is linearly dependent in this one? Well, in this, yes. In this setup, the way that we have it written, yes. Now, what if I were to interchange two of these columns? What if I were to like swap these two? Well, there's a good chance that this column then would be considered the linearly dependent one if you swap it. So the position that they start in certainly determines whether or not they form the basis vectors or not. So yeah. So notice how we always have a pivot in the first column. So by having that pivot there, that means that this first vector is going to be linearly independent, as long as you don't have a 0. If you have a 0 in this first position, then that vector may not be linearly independent. But okay, so now what? We need to find the null space. So let's go ahead and copy this. Can I take this whole matrix? Let's see. Copy. We'll bring it down here. This may not work. Paste. Aha! All right, it worked. Lucky me. We'll shrink it down here. And so now we're going to have to use this row-reduced form of A to help us find the null space. Basically, we want to find the general solution. So the general solution we'll write it like this. I've lost my cursor again. I'm going to have to restart it. It's kind of a pain. Every time I lose my cursor, I've got to restart just because I can't tell where I'm writing. Okay, here we go. General solution is going to be, let's see, so we want to write our free variables. So x2, x3 is free, and x4 is free. So we want to write all of our x5 is free. We want to write all of our basic variables in terms of our free. So x1 is a basic, is going to be equal to negative x3 minus x5. x2 is a basic variable, and it's going to be written in terms of 2x3s and minus 3x5. Remember, I'm subtracting or adding these to the other side of the equation, so we are always taking the opposite sign. x3 is free. x4 is another basic, so this is going to be written as negative 5x5, and then x5 is free. Okay, so now a solution vector, x1, x2, x3, x4, and x5. This is what we did in chapter 1. We can just write this out as negative x3 minus x5, 2x3 minus 3x5, x3, negative x5, 5x5, and then x5. And so now we want to break this up into x3s and x5s. So we have negative 1, 2, 1, 0, 0. This is for x3. And then we want x5 is -1, -3, 0, -5, 1. And this is for x5. And so now we have basis for null A is the span of these two vectors. So, or null A is the span of these two vectors. Notice that the dimension is now, they come from R5. It's because they need to be compatible with multiplication for the matrix. Okay, there we go. So let's just kind of check our answer. So the dimension of the column space of A is the number of linearly independent columns is 3 equals the number of linearly independent rows. So the row space and the column space should have the same dimension. They each have 3 linearly independent columns and rows. So this means that this is going to be equal to the rank. So the rank of A is 3. So what is the dimension of the null space? So dimension of null A is here. We have 1, 2 linearly independent vectors. So it's going to be 2. And then if I add the rank of A, add to the dimension of the null space. So sometimes the dimension of the null space is called nullity. We're going to get 3 plus 2, which is 5, which this is the number of columns. Okay, so this is the rank theorem. Okay, there we go. Cool. So let's see, we did everything that they asked for there, I think. We even did more. We used the rank theorem. We'll probably have to use this on the next page, I'd imagine. Example 3 here says, part A, if A is a 7 by 9 matrix with two-dimensional null space, what is the rank of A? So maybe I'm going to pause the video here. What do you think that the rank of A is? Maybe type it in the chat real quick. I'll pause. So here, the answer is 7. You have 7 linearly independent columns. 2 of these columns correspond to free variables, since the null space is two-dimensional, and the other 7 columns correspond to pivot columns, which means the rank is 7. Okay, so now part B, let's do the same thing. It says, could a 6 by 9 matrix have a two-dimensional null space? So think about that and record this. So the answer here is no. So let's look. So we've got a 6 by 9 matrix. I could draw 9 columns again. And there's only 6 rows. So think about the 6 rows here. That means that a maximum of 6 of these columns can be pivot columns. You can't have any more pivots than you do rows because you run out of rows at some point. So that means that 3 of these are going to be free variables, which means a minimum number of free variables is 3, which implies the nullity or the dimension of null A is going to be, I'll say, greater than or equal to 3. Yeah, so that would be the idea or the logic behind the argument. So six pivots maximum, 3 free variables minimum for that problem. Okay, let's keep rolling. What do we have here? Let A equal this 3 by 3 matrix. Find and consider the subspaces determined by each one of these. Null A, column A, row A, and row A transpose. Describe these subspaces inside vector space R3. Sure. So all of them, by the way, are going to be subspaces of R3 automatically. All right, well, here we go. So all of these, let's start with the hard one. Let's start with null A. So let's find, we have 2 free variables, x2 and it will, if one free variable, if we start row reducing here, we're going to get something. Let's see, can I do this quickly? Um, let's do A, and then I'll eliminate the second row, get a 1 here, and then we'll get a 6 here, and then we'll eliminate that 3 with the 1, and in order to do that, we're going to have to subtract it 3 times, which is going to give me a negative 19 there, and then we'll swap a bunch of these rows to get 1, 0, 6, 0, 0, negative 19, and then you could just normalize that middle row to get a 1 in that position. So this is going to be, so I just did a quick row reduction there, that's a 6, and then you have 0, 0, 1. Okay, so here we can see something pretty clearly. You can even eliminate that 6 there if you wanted to keep going. Let's go ahead and do that to get to reduced row echelon form. So we can see that x2 is a free variable. We could see that from the beginning because we had a column of zeros. And x3 is a basic variable and x1 is a basic variable. So if I want to find the null space, we can say x is going to be, let's see, we have 0 x2s, and so it's just 0. x1 is 0, x2 is free, and then x3 is 0 as well. And so then we have just the null space of A equals the span of just one singular vector, 0, 1, 0, just like that. So the dimension of the null space, you could say nullity of A is equal to 1. So they want us to describe these subspaces. So this is just a one-dimensional subspace. It's just a line. So this is a line in R3. Okay, because the span of a single vector in 3 space is just going to produce a line in this direction along the y-axis, if we were thinking about in terms of x, y, and z. So now we'll use this reduced row echelon form right here to help us find the basis for the column space and row space. So column space of A is equal to the span. Let's find the columns. So we want to correspond these pivot columns back to the original columns. So these are the 2 linearly independent columns. So 3, 3, and 4, and -1, -1, and 5. So that would be the basis for the column space. And now the row space is the span of these 2 rows. Remember, in the reduced row echelon form, you can just take these rows. So the first row looks like this, 1, 0, 0, and I'll transpose that so that it's a row. And the second row, this one right here, is just 0, 0, 1, and we'll transpose that. So this gives me the entire row space. Okay, so then we have the dimension of col A equal 2, and the dimension of row A is also 2. And then they want the dimension of row A transpose. So let's go ahead and transpose A. So A transpose is going to be 3, 3, 4, 0, 0, 0, -1, -1, 1, 5. Just like that. And so if I start row reducing this, we're going to be able to eliminate those 3's in the top. So it's going to be 0, 0. I have to add 3 of them, so this is going to be a 20, add 3, 15 to that, so 19. And then we have -1, -1, 5. And then I can use that 19 to eliminate the 5, so we get 1, 1, 0, and then 0, 0, 1, and a row of zeros. So row A transpose, something doesn't feel right about that. Did I mess something up? No, I think I did that fine. Yep, So then now if I do the basis for row A transpose, we're just going to get the span of 1, 1, 0 transpose and 0, 0, 1 transpose. Okay, so row A transpose is not the same thing as the column space, at least that we can tell. It might be. If I'm looking at these two, can I produce the? It is the same thing as the column space here, just with row vectors instead of column vectors. But it produces the same type of information. So we could have just said at the beginning the span of this vector transpose and this vector transpose, because they are linearly independent vectors, but regardless. So here, this implies, these two together imply that the rank of A is 2, and the nullity is 1. Sum of the rank and nullity is 3, which is the dimension of the overarching space that they come from. And let's see, they say describe these spaces. So all of these form planes. Form planes in R3. Okay, good. Let's keep on rolling so that we don't run out of time here. Example 5 says a scientist found 2 solutions to a homogeneous system of 40 equations and 42 variables. It says the two solutions are not multiples, and all other solutions can be constructed by adding together multiples of the 2 solutions. Can the scientist be certain that an associated non-homogeneous system has a solution? So AX equals 0 has two solutions that are not multiples. So 2 solutions. Not multiples. And they want to know AX equal B. This is a non-homogeneous system. Does this have a solution? So I'm going to pause the video. What do you think? Let me record this. So the answer is yes, you can be sure. So maybe I'll say yes. Every non-homogeneous system has a solution. And if you wanted to give a little bit more reasoning, you could say because the minimum dimension of null, the null space, is so it's going to be greater than or equal to 2, and we know the dimension of the null space because they gave us the number of vectors that span the null space is 2, which implies the dimension of the column space. So let's use the rank theorem here. So we'll say rank of A plus dimension of null A must equal 42, the number of columns, and we know that this is 2. So that implies that the rank of A is 40, which means that every single solution, or every single non-homogeneous equation must have a solution because there are 40 rows and 40 pivots. 40 pivots implies that it spans R40, and so if you take a random vector B inside R40, then it's going to be inside the span of the columns, the column space, just because you don't have enough free variables for it to not be. So the null space isn't large enough. Yeah, okay. So that's a really convoluted, weird problem, but it's a good one to illustrate what we're learning. Okay, well, good. We're approaching the end of our time here, but I need to finish recording this. So we have a short section here on the change of basis. So what I'm going to do real quick is I'm going to record the attendance, just in case some of you have to leave. So let me pause the video and record attendance. Okay, so let's go ahead and talk about change of basis. So we've learned that you can have a basis for a space, and then you can have another basis for a space, so two unique bases for the same space. Well then, is there a way to change back and forth between the two bases? And that matrix is called the change of basis matrix. And so that's what we're going to talk about in this section here. And the way that you find it is by changing one basis into, change each one of the basis vectors, find the weights for each one of the columns, and choose those. These are called the C coordinates of B1, the C coordinates of B2. So we found how to find these in one of the previous sections. And you slap these as the columns of the matrix, and this is called the change of basis matrix from B to C. Now notice the direction here. The direction is going from B to C. So this matrix, if you multiply a vector, well, I've got it written right here. If you multiply a vector inside B coordinates, it changes it to C coordinates. So this is a very useful change of basis matrix. You could also view it as like warping the space, or maybe, yeah, kind of like our UV transformations that we were doing in multivariable, where you're changing the space only in the linear sense, though. So we can't really warp it in a non-linear sense. Okay, so let's go ahead and look at an example here. So they want me to find the C coordinates of this vector x. So what we're going to do is use this change. We have this change of basis, or we have B1, the basis, first basis, written in terms of C1 and C2. This is the second basis. And so we can write the C coordinates of B1. That's going to be 4, 1. And we can write the C coordinates of B2. That's going to be negative 1, 1. And so now P going from B to C, so if I change the coordinates from B to C, that's going to be B1 written in terms of C, B2 written in terms of C, and that's going to be 4, 1, and negative 1, 1. And then now we can multiply any vector's B coordinates by this matrix to get its C coordinates. So we'll write the vector x. Its B coordinates are going to be 3, 1. And now we'll just say x's C coordinates, which is what we were looking for, is going to be this matrix P going from B to C, multiplied by the B coordinates of x, which is going to be 4, 1, negative 1, 1, multiplied by 3, 1. So let's see, what do we get here? That's going to be 12 minus 1, or 11, and 3 plus 1 is 4. Okay, so this is the C coordinates of x. So x equals 11C1 and 4C2. So that's what these coordinates here imply, that we have 11 of the first vector and 4 of the second vector. Now, you could also try this by directly plugging these in here. So let's check our answer. So we're going to say x is given to be 3b1 plus b2. And if I replace b1 with 4c1 plus c2, and replace b2 with negative c1, right here is where I'm looking, plus c2, we're going to get 12c1, c2 minus c1 plus c2. So we get a total of 11c1 and 2, let's see, oh, this is 3. Distribute for 3. And then 4c2. So you could find it that way, or by finding the change of basis matrix. So the change of basis matrix is really what we want to talk about here. That's the principle of what we're learning. So let's try another one. Let's get down to earth a little bit. Let's do one that's concrete here. So they say find the change of basis matrix. So what we want to do is find the C coordinates of B1. So we want to find, let's see, so what letters do I want to use? I could use C and D. C is a little awkward to use here. C1, D, C2, something like that. So you have B1 written in terms of C1 and C2. And this would give me the C coordinates of B1. And then we want to do the same thing for B2. We want to find E, C1, and F, C2. Well, now the row operations that we're going to have to do for each one of these are going to be identical. So I would have to row reduce a matrix C1, C2, and B1 to find the C coordinates for B1, and then I'd have to row reduce the exact same matrix to find the C coordinates for B2. So instead of doing two row operations, we can actually combine the row operations to be done simultaneously. So we can do C1, C2, and then augment that with B1 and B2, and then row reduce. So let's go ahead and do that. So this is going to be 1, -4, 3, -5. This is C1, C2. And then here's B1 and B2. And then we'll start row reducing. So let's eliminate that -4. So that's going to be 12 onto the 5, so 6. And then that's going to be negative, what is that? 36, so -35. And then that's a 5. And then we'll do 20, so -21. Let's see, so is this really a 6 or is it a 7? Because it'd be nice if it was a 7. So let's double check that. I'm adding 12 onto the 5. It's a 7. It's a 7. I did my subtraction wrong there. So then we'll want to divide that second row by 7. And then we'll eliminate the elements above it. So let's eliminate the 3 by subtracting 3 of them. So that's adding 15 to -9. And then we'll add 9 to -5, so that's a 4. Just like that. Okay. So what do we have here? So now this on the left is the identity, and on the right we have B1's C coordinates and B2's C coordinates. So if I take 6C1, so we could write B1 equals 6C1 minus 5C2, and B2 is equal to, we want to look at this column right here, 4C1 and -3C2. There we go. So this is our change of basis matrix. So on the right hand here on the left we have identity, on the right we have P going from B to C. Okay, so that's all they wanted. So P going from B to C is equal to 6, 4, -5, and -3. So this is how you would actually find the change of basis matrix. It's a lot like finding an inverse matrix. If you remember, what we would do is we put the identity on the right and row reduce to find it. Well, this is exactly the same thing. It's just that we're not starting with the identity. Instead, we're starting with one basis and trying to find the row operations to get to the other basis. And so those row operations end up producing the change of coordinate matrix, P going from B to C. If you want the other direction, you would have to augment originally. You'd have to put the B's on the left and the C's on the right. So here, this is helpful because it's going from B to C. And if you wanted the going from C to B, you would have to put the b's on the left and the c's on the right. So this notation is actually quite helpful because it helps you remember what direction things are supposed to go, and it also helps you remember what direction you're supposed to feed things. So I'm supposed to feed vectors on the right side in terms of b, and this will change vectors to vectors in terms of c. So this notation is a little awkward because it's arrow pointing to the left, but it's definitely helpful when it comes to setting it up and solving. Okay, so maybe we won't have time for both of these, but let's just try one and then we'll be done here. So is this the same basis as before? No, these are different bases. Let's just find, we already did p going from b to c, so let's do this one. So let's augment the b vectors on the left this time, and the c vectors on the right. And then we'll row reduce. You can use a calculator, but here this one doesn't look too hard. It's going to be -5. I think, and then -3. Oh, really? 5/2? Did I do something wrong? 1, 2, 3. Oh, 21. I did do something wrong. So let's see. I'm subtracting 21 from the 9. So that's going to take me down to 12 negative. And then this one's going to be 15 and 7, so that's a -8. Okay, there we go, that's better. So this is going to be a 6, and this is a 4. Okay, so I thought something seemed fishy there. So add the 12 to the 7 to get 5, and then add the 8 to the 5 to get 3. Okay, so here it is. So this is the identity on the left, and the matrix on the right is P going from, remember we started with C's on the right here and B's on the left. So this is going from C to B. Okay, and you might make a guess. You might make a guess and say, well, wait a second, wouldn't these matrices be inverses of each other, right? If I row reduce one to get the identity on the left and row reduce the other to get the identity on the left, wouldn't they be inverses? And the answer is yes. So P going from B to C is just going to be P going from C to B inverse. So let's just take the inverse of this. So the determinant is going to be 20 minus 18. Swap these two, so 4 and 5. Negate the others. So then we're going to get 1/2 for -3, 6, 5. Just like that. Yeah. So there's the two matrices. One going P from B to C, and the other going from C to B. Okay, I think that's probably where I'm going to stop. I don't want to prolong. I mean, I can do this last example, but if you guys, I'll do it. Let's do it. I'm sorry, I want to do it. I don't want to take up your time though. So if you really have to go, you go. But here we go. So let's do this last one. They want us to find the B coordinates of x and the C coordinates of x. So let's go ahead and do that. So right now, this is not in either of the bases. So what we're going to have to do is do B1, B2, and augment that with x, and row reduce to find the B coordinates of x. So let's go ahead and do that. So here's B, B1 and B2. Here's x. We'll row reduce. So I had to add 3, so it's going to be 1 and a 6. -5. And then this is going to be a 1 and a -3. Okay, so what did we just find here? This is on the left, this is the identity. And on the right, this is the b coordinates of x. Okay, so now that we have that, let's just use our inverse matrix from up here to take the b coordinates of x to find the c coordinates of x. So we'll say p going from b to c, and we'll multiply that to x, the b coordinates of x. So this one is got the 1/2 out in front. And then we can multiply it to this vector, -5, -3. We're going to get -20 plus 9 is -11. Did I do that right? Let's just double check. -20 plus 9, yeah, is -11. Then we got -30 and minus another 15. -45. That's nice and ugly there. Something does not feel right about that. Well, we have a way to check our answers. So this is presumably the c coordinates of x. So the way that we could check this is to augment c1 and c2 with x and then row reduce. So let's go ahead and try that. Uh-oh, so some of you have caught my error. 6 would be negative in the inverse. This is this one right here, the negative. In the inverse. Oh, in the inverse. This is a negative. That's a negative. So it's a positive 30. Thank you. Oops, I missed my negative there. It's a positive 30 and a negative 15. So we get 15. We get positive 15 here. Is that what you guys are saying? Yes, okay. Good catch, you guys. Okay. So, good. So let's still check our answer, though. Let's go through this. So what was C? So C is -7, 9. And I think -5, 7 or something like that. Yeah. Okay, so then we'll do 1, 3. And then just start going hog wild, row reducing here. We'll divide that bottom row by 2. And then we'll eliminate the 7 by adding 7 to the row below it. So that's going to put a 2 here. And that's going to put a 14 plus 1, 15 right there. And this is a 2 still. And then we'll swap the rows and maybe divide that by 2. So this is going to be a 15 over 2. And this is going to be a 0. Subtract 15 over 2 from 2. 2 is the same thing as 4 over 2. Take away 15 is -11 over 2. So this is going to be 1, 0, 0, 1. 11, -11 over 2, -15 over 2, which is what we got, surprisingly. So we did it okay. So our answer checks out. So what this tells me is the c coordinates of x is -11, -15. We didn't have a negative, though, did we? We had a positive there. So did I make a mistake here? Let's just double check our work. I got the right numbers, but oh, that was a positive 15. That was a positive 15. And a 1/2. Yeah, so our answer checks out there. We did get the correct answer. Yeah, so hopefully that made sense to you guys. Thank you for sticking around and watching. I will post this up online for those that are taking exams. And I did go 10 minutes over, but for those of you that are taking exams this week, good luck. And I'll see you guys next week.